Dear students, in this particular lecture we are going to discuss about Maxwell's equation in integral form as well as Maxwell's equation in differential form. So here we first start with Maxwell's equation in integral form. So what is Maxwell's first equation? Maxwell's first equation is simply Gauss's law of electrostatics. Gauss's law in electrostatics, which you already learned in your 12th board days. In class 12 we learned that surface integral of E dot ds is equal to 1 by epsilon 0 times the charge enclosed by the surface, that is total electric flux through any closed surface equals to the net charge inside that surface divided by epsilon 0. So what is the physical significance, or what is the physics of this Gauss's law in electrostatics? So this law gives us a relation between electric field and charge distribution. Electric field starts from positive charge and it ends at negative charge. In fact, your Gauss's law is equivalent to Coulomb's inverse square law in electrostatics. Gauss's law in fact is true because we have Coulomb's inverse square law. You can say it is in form coming from Coulomb's law itself. So Gauss's law of electrostatics is your first Maxwell equation. Next we will move to next law. Next law is again Gauss's law of electromagnetism, or you can say Gauss's law of magnetism. Here Gauss's law of magnetism, its left side, you will see that here you have surface integral of E dot ds. First of all, on closed surface you will have to choose. Here also in this first law you have a closed surface. Here also you take a closed surface and you take surface integral of B dot ds. B means here magnetic field, but that turns out to be 0 here. So the statement is that net magnetic flux through a closed surface is 0. This is Gauss's law of magnetism. Why is it so? Because number of magnetic field lines entering closed surface is equal to the number of field lines leaving the surface. It also implies that isolated monopoles do not exist, since isolated magnetic monopoles are not observed also experimentally. So this law stands confirmed. So the basic idea behind this Gauss's law of magnetism is that net magnetic flux through a closed surface is 0. So let me show you by a diagram. Suppose you have a surface here. This is a loop, this is a surface. So if you draw magnetic field lines, suppose two field lines enter, then two field lines come out also. That is the property of magnetic field. So net flux is 0. If net flux is there, then number of field lines entering will not be same as number of field lines leaving. This happens in case of electrostatics, and that is why the right hand side of E dot ds is non-zero, but in this case it is 0. So this is also discussed in your class 12. So we'll move on to the third equation. Third equation is simply Faraday's law of electromagnetic induction. You know Faraday's law of electromagnetic induction. It tells that whenever there is a change in magnetic flux linked with a closed circuit, then or a closed loop, then there is a magnetic, and there is an electric current set up there. But if you have closed loop, then you will get current. But if your loop is not closed, then you will get an induced EMF. So Faraday's law is simply production of it is linked with production of induced EMF in a circuit if there is a change in magnetic flux linked with this circuit. And you also learn that induced EMF E is equal to negative time rate of change of magnetic flux. Here 5e represents magnetic flux. Now you will see that in equation 3 it is written as line integration of E dot dl equals to minus d5e dt. What does this line integration of E dot dl represent? So to go to this, we again go to this diagram. In your electrostatic chapter, you will find that electric field is linked with electric potential. This E means electric field and this V means electric potential by the relationship B equals to negative integration E dot dl. So this relation E dot dl integrated line integration of E dot dl in fact gives us electric potential V. So if we draw that equation here, if you bring that equation context here, then line integration of E dot dl simply represents EMF E. This EMF E, line integration of E dot dl is EMF E. So this is our Faraday's law of electromagnetic induction. Line integration of E dot dl equal to minus d5v dt. So what does it tell? According to this law, the line integral of electric field around any closed path, that is which we call as EMF, is equal to rate of change of magnetic flux through any surface bounded by that. So again I will show you the diagram. That is, suppose you have this loop and this is the surface. So line integration of E dot dl over this surface, line integration of electric field over this surface which has the closed path is equal to rate of change of magnetic flux through any surface bounded by that. So this is your loop and this loop bounds this surface as line integration of E dot dl over this loop is equal to rate of change of magnetic flux which cuts through this surface S. Next, let us move on to fourth law, Maxwell's fourth equation, you can say. So Maxwell's fourth equation is simply the modified Ampere Maxwell law, which we discussed in last lecture. In last lecture, I showed you that line integration of B dot dl is equal to mu0 multiplied by I plus Id. I is known as conduction current and Id is known as displacement current. And when you put the expression for displacement current, which is equal to epsilon 0 multiplied by d phi dt, d phi dt, phi represents electric flux here. So this comes out to be line integration of B dot dl is equal to mu0 I plus epsilon 0 mu0 d phi dt. So this is the mathematical statement of Maxwell's fourth equation. And what does it indicate, or what does it state? It states that line integral of magnetic field around any closed path is determined by the sum of net conduction current through that path and the rate of change of flux through any surface bounded by that path. So this law gives us an important thing, that a magnetic field can be produced by a changing electric flux as well as conduction current. Before that modification by Maxwell, it was thought that a magnetic field could only be produced by conduction current, but presence of this term indicates that a magnetic field can be produced by both changing electric flux and a conduction current. So Maxwell's fourth equation is statement of Ampere's Maxwell law. So if you have a look at all these four equations, you will see that all these equations are somehow discussed in class 12 chapters. You learn about Gauss's law in electrostatics. You also learn Gauss's law of magnetism in class 12. You also learn Faraday's law of electromagnetic induction. However, you might not be able to interpret it in terms of line integration of E dot dl. And this one is also learned the modified Ampere Maxwell law in class 12. So in examination, if you're asked to tell or what are physical significance of Maxwell's equation, you write the significances which are given at the end of these equations, 1, 2, whatever is given in this particular page. These significances are there at the bottom. Next, let us try to convert these equations in differential form. You will note that all these equations have integral sign on the left hand side. All the four which I have shown here: first, second, third, and fourth. Can we convert into differential form? The differential forms are also handy, particularly when we go to derive the expressions for electromagnetic waves. Then the Maxwell's equations in differential form are very important. So let us try to give an insight how to convert Maxwell's equation in differential form. So first, let us start with that Gauss's law. That is, surface integration of E dot ds is 1 by epsilon 0 times q. So we take the first equation here, and you have a surface that encloses a volume V. So you have a surface here, this surface S, and it encloses a volume V. Now we have surface integral of E dot ds 1 by epsilon 0. This q is replaced by rho dv. We already discussed and we showed in last lecture also that during equation of continuity, that q can be replaced by volume integration of rho dv, where rho is your charge density. So as you move forward, we will see that here the replacement of surface integration of E dot ds, this is done by a volume integral. How? There is Gauss's divergence theorem to give us that freedom. We have surface integration of A dot ds. A is any vector, is volume integral of divergence of A multiplied by dv. Again I repeat that here it is divergence of A dv, there is no dot here, and volume integration of del dot A. Del dot A, another way of writing this. Divergence can be written as di of A or del dot A. So when you write here, then we have volume integration of del dot E dv, surface integration of E dot ds converts to that. Right hand side remains the same. You do make a transpose, that is take this to left hand side and do a simplification. You put the dv out, take this other thing common, and Now let us concentrate on this line. What does it line this line to this line? So here we have written volume integral epsilon 0 del dot E minus rho dV equals to 0. From there we have written epsilon 0 del dot E minus rho equals to 0. How? The answer is we took a surface S which enclosed a volume V. This surface was enclosing a volume V here. So the surface, we did not specify any specific surface, neither we specify what was the volume of the surface. So when you are getting this volume integration of epsilon 0 del dot E minus rho into dV equals to 0, this dV is arbitrary volume. So this result, volume integration of epsilon 0 del dot E minus rho dV equals to 0, is true for any arbitrary volume. Since it is true for any arbitrary volume, this integration, if the result of this integration comes out to be 0 for any arbitrary volume, it is only possible if this integrand, this part, epsilon 0 del dot E minus rho equals to 0. Otherwise, it's not possible. So volume integration of epsilon 0 del dot E minus rho dV equals to 0 is possible for arbitrary dV only when epsilon 0 del dot E minus rho, that is the integrand, is itself 0. From there I can arrange and I can simply write it in this form: epsilon 0 del dot E equals to rho, del dot E equals to rho by epsilon 0. So this is your Gauss's law of electrostatics in differential form. Now let us go to second one. We want to establish that second law, which is your Gauss's law of magnetism in differential form. So we'll start with that simple thing, that we have that integration of B dot ds equals to 0. Here it's a mistake. It should be as surface integration of B dot ds equals to 0, because the total outward flux of magnetic field B through any closed surface is equal to 0. Surface integration of B dot as ds equals to 0. That is your Maxwell's second equation. Now, using Gauss's divergence theorem, you can convert surface integration to volume integration. So surface integration of B dot ds will become volume integration of divergence of B. Here it's not, should not be comma, it should be a dot here. Volume integration of del dot V dV equals to 0. Now again, by the previous logic which we used in that derivation of 1 differential form 1 Gauss's law, here volume is arbitrary, this dV is arbitrary. So volume integration of del dot B dV is equal to 0 is possible for this arbitrary volume dV under only one condition, that is your this integrand del dot B is 0. So this is Gauss's law of magnetism. And remember, Gauss's law of magnetism del dot B equal to 0 represents magnetic monopoles do not exist. Magnetic monopoles, yes, do not exist. Then we will try to move on to next law, which is Faraday's law of electromagnetic induction. How to convert it into a differential form. So you know that induced EMF E is equal to minus d phi dt, and induced EMF E is also line integration of E dot dl. The magnetic flux is given by surface integration of B dot ds, this magnetic flux expression. It is also coming from your class 12. B dot ds represents magnetic flux for the entire surface. Again, I would like to tell you that here also you have a loop, and S is the surface which bounds that loop in this case. So this B dot ds for this surface is taken, which is your phi surface integral, and line integration is taken over this boundary of this loop. Line integration of E dot dl, that is equal to the induced EMF E. Then you see that going back to equation 1, which is your E equals to minus d phi dt, we replace this E induced EMF by this equation 2, which is line integration of E dot dl, and we will replace this phi by surface integration of B dot ds. By doing so, you are going to get this E dot dl, which is your induced EMF, is equal to minus d dt of B dot ds. We can put this d dt inside this surface integral, because the surface integral is not changing with time. So I can write minus surface integration of dB dt dot ds. Again, here this derivative, full derivative, is converted to partial derivative. Why? Because we are interested only in the change of B over the small area element ds in this equation. And here magnetic field varies, variation with time is relevant, other variation are taken to be constant, or they are not at all important here. So here, that is why you have dV dt replaced by del B del t. So we have E dot dl now is equal to minus surface integration of del B del t dot ds. Again, to bring it in a common platform, you need Stokes theorem. This line integral we need to bring into something else. How? Let us see. This line integration of E dot dl can be converted into surface integral. We have Stokes theorem, which says that line integration of A dot dl is surface integration of curl of A dot ds. So here we have the equation modified like this. Line integration of E dot dl is replaced by surface integral. This factorial sign is an error here. Surface integration of curl of E dot ds, which is equal to minus integration of del B del t dot ds, which will imply, here again it is implied, which will imply surface integration of curl of E plus del B del t dot ds equals to 0. So this one comes very in a simple way. And since this equation is true for any surface, here we have a loop and we have a surface, but the loop is arbitrary, surface is also arbitrary. So this surface integration of curl of E plus del B del t dot ds is equal to 0, and that is 0 for any surface field. So that is why you can write that curl of E plus del B del t equals to 0. So since it is 0 here, by the previous logic, integrand must be 0. We have curl of E coming out to be minus del B del t. This is known as Faraday's law of electromagnetic induction. Now we will go to the fourth Maxwell's equation, and its differential form. So we start with the integral form. Line integration of v dot dl is equal to mu0 times I plus id. I is your conduction current density and id is your conduction current, and id is your displacement current. So when you go for this, you will find that we can have a current density for conduction current, and we can have a current density for displacement current also. So current I is replaced in terms of current density. I is equal to surface integration of j dot ds plus again surface integration of jd dot ds. So again on the left hand side you will see that line integration of b dot dl, that one is replaced by surface integration of curl of b dot ds by Stokes theorem, which we are using several times. Line integration of a dot dl is equal to surface integration of curl of a dot ds. So this is done in the left hand side, conversion of line integral to surface integral. What is done in right hand side? Right hand side, it is merged together. ds dot ds is taken other way. Thereafter we transposed this to left hand side and we made surface integration of curl of b minus mu0 j plus jd dot ds equals to 0. We have a dot here, you have to remember it. Next, what we do is that we can write curl of b minus mu0 j plus jd equals to 0. By the logic is that we have a surface, we have a loop, and we have a surface where ds is arbitrary. You have chosen any surface, this is true for any surface, and this integration will be 0 for any arbitrary ds only when curl of b minus mu0 j plus jd is 0. So on transposing, curl of b equals to mu0 j plus jd, and curl of b can be written as mu0 j plus epsilon 0 del E del t. How this arrives? This is shown here. We have displacement current id is equal to epsilon 0 d phi dt. Then since we are interested exclusively with that flux change with time, so we replace del t instead of ddt, and flux phi is E into A of that capacitor plate expression. It can be something else also, but for the time being, for simplicity, let us take it to be epsilon into A expression, and here this epsilon 0 A is taken out because electric field is varying with time but area remains constant here. So id by A is epsilon 0 del E del t. Now what is id by A? It is your displacement current density, and you will see that we have inserted vector sign here. jd is equal to epsilon 0 del E del t, but one line is not shown here. In scalar form I have not written directly, I have written id by A is in vector form. So jd is simply epsilon 0 del E del t, and this is your boxed one, curl of b equals to mu0 j plus epsilon 0 del E del t. This is your Maxwell's fourth equation in differential form. So at the end of this lecture, I would like to request you to see other forms of these equations, we did not go into H form instead of B. Some books they go with H form instead of this epsilon 0 del E del T. They introduced D, electric displacement vector. But since here, as per your syllabus, you are asked to learn basics of Maxwell's equation, so we have tried to be as precise as possible with as much as simplicity. So that is the main basic objective in this lecture, to get these equations in a simple way. So with this, we wind up this lecture, and what we learned Maxwell's equations in integral form as well as conversion of the equations in differential form.